Hi everyone, this video will show you how you can go and find G-Power and then install it in your computer. Afterwards, what we will do is to run some power analysis for correlation and for regression. The first thing that I did, as you can see here, is to enter G-Power in your search engine. In my case, I use DuckDuckGo, and then I had several hits. The one that I want to select is the one that is related to the University of Düsseldorf, because that is where the program was developed. So I'm gonna click on this option and it will take me to a new page. This is the new page where I landed after clicking OK. And then you can see that here we have an option for G-Power. If you scroll down, you will see that you have a few things that we need to download. Here we have the G-Power manual and the short tutorial for G-Power. I already downloaded these two. And then below, you will see that you have an option for downloading either G-Power for Windows or for the Mac. In this case, because I am using a Windows 10 computer, I'm going to click on G-Power for Windows, but you can click on the G-Power for Mac. I have used this in my Mac and it works fine. So I click on it and it will save the file. That's what you need to do next. After it ended downloading, I moved the file to a folder that in my computer I am calling G-Power. You can see that here. And I also downloaded the two manuals that we are supposed to be using to understand more about how to use G-Power. Notice that in my computer it created a zip file. If you are downloading this to a Mac, it may also this may be slightly different, but in general it will be very similar to what you see here. So I'm going to click on this option, and what you can see is that it opens a new folder called G-Power 3.14. I click on that again, and then you can see that here there is a setup option. You can see that there are a few files here, and I'm going to click on the README so you can see some of the things that you are agreeing to if you decide to use G-Power. So this is the file that opens, and you can see that it basically says that G-Power is free for all the users, and that if you want to distribute this from your own website, you need to ask permission. Otherwise, you need to download the file always from this website. And if you want to have some kind of support, you need to send a registration to this website. Also, it speaks about how you need to include the reference for G-Power whenever that you are using this program. And here it speaks about what will be the reference that you're supposed to be using. Please be kind to the authors, and whenever that you are using G-Power, make sure that you are making reference to the program. Okay, so we are back in my folder, and what I need to do next is to click on Setup. But before I do that, I need to make sure that I move this file and all of the files outside the zip file, because otherwise it will not be able to run. So what I'm going to do is move back to this folder called G-Power 3194 and move it to G-Power. And after I do that, you can see that now I have a new folder called G-Power. I click on it, and then I can click on Setup and Install. There is going to be some routines that need to be installed. The program may ask you to install some default program so it will run. Just make sure that you follow all of the defaults and that you click on Next every time that it asks you for, and eventually it will get to this point where it says installation complete and that is ready to run. So once that we have that, we're gonna close and we will be ready to start using it. In your computer, now you will find that in the menu you have a new program called G-Power. So just click on that G-Power program and you will be ready to start running the program. So this is what G-Power looks like after you open it. So before we start playing with G-Power, let me give you a general orientation to the different windows and menus that you have available. In general, using G-Power is very straightforward. You can see that you have several menus at the top. You have File, you have Edit, View. Test is the one that we want to be especially related to, because you can see that under Test you have several options. We have correlation and regression, we have means, proportions, variances, and genetic. In our case, we will be concentrating exclusively on the correlation and regression option. So we were saying that we were going to spend all of our time looking at the menu related to correlation and regression. We will go over several of these options, but I will not cover every one of these in this video or in any video. If you are interested to learning more about how to use G-Power with some of the options that we are not going to cover, like for example Poisson regression, then please follow some of the information that you may find online. You can see that in addition to the menus that you have at the top, you also have some other menus here. You have test family, you can have the statistical test. You can see that here we have some of the similar options that we had before, but some of them are different. So my suggestion will be that you go rather to this test to this menu that you have at the top. Some other things that you have here are the type of power analysis. I will describe some of these options so you can have a better understanding of the options that may be more important for you whenever that you are ready to run some power. And then here you will have some results. So this is where it's going to be putting some of the values that we need to calculate. So we're going to start by going over the correlations. So you can see that here we have three different types of correlations. Bivariate, so this will be our Pearson correlation. We have the point biserial model, so this is one of the correlations you might remember that we covered. And the tetrachoric model, I mentioned in one of the lectures that this is the same kind of model as if you had two nominal variables. In this case, it can be expanded to more than two correlations. Next, you may remember that we were looking at some of these options here. This is for when we have two correlations and we want to do some testing. So here we have two dependent Pearson correlations where we are trying to assume that one of the variables is the same for the two correlations. This is for when you have two dependent Pearson correlations but you do not have any common index, and this is if you have two independent Pearson correlations. You might remember that we were looking at an Excel file that allows you to calculate some of these numbers. So now not only you have a way to test them, but you also have a way to estimate the power associated with that. Next, we have the linear models. This is for when you have one independent variable, and this is for when you have multiple regression model, which is you have several independent variables. Finally, we have the logistic regression. If we have some time after we cover logistic regression, we will come back and look at how to estimate some power for this type of models. So let's start playing with correlations. We're going to start by testing a correlation, and we're going to be doing a bivariate normal model, in other words, a Pearson correlation. As you can see here, we have several options that we need to understand. One of them that is very important for us will be a priori. So what we are doing in this case is assuming that we don't have any data yet, and instead what we want to be able to know is what will happen, what will be the sample size that we will need given a specific alpha, power, and effect size. The only other option that we are going to be reviewing is what is known as post hoc. And in that case, what we will do is to check if what was the power that we were able to get after we set the alpha, the sample size, and the effect size. The reason we are going to be spending time only on those two options is because every time that we are interested in checking the power of some specific model, those are the options that we find more important. We either want to know what is the sample size that we need to get in order to have a significant result, or if we want to know what was the power that we were able to achieve after we ran an analysis. The way that the program was conceived many years ago was based on the work of Cohen and Cohen, and because of that, what I decided to do is to give you a reading from Cohen and Cohen, and you will find that information in the materials for this week. So, because we are using, or the authors of G-Power were using Cohen and Cohen as their guideline, we're going to be looking at examples in the way that Cohen and Cohen suggested that you need to calculate power. So as you can see on the screen, I have an example of how power will be defined by using Cohen and Cohen's approach. We start by speaking about effect sizes, and you can see that according to Cohen and Cohen, they speak about three effect sizes. For correlations, they spoke about the fact that a high effect size will be a correlation of 0.5. For medium effect size, they suggested to use a correlation of 0.3. If for low effect sizes, they suggest that you use a correlation of 0.1. Next, the things that we need to do is, if we are interested in calculating a sample size, how big needs to be my sample size, then here are the steps that they suggest. The first thing that we need to do is to determine the effect size. In other words, what will be the population value, what will be the correlation in the population. Then we will set the alpha value and whether it is a 1 or a 2-tail test. And finally, we will determine the power. Usually Cohen and Cohen suggested to use as point A as the standard value. So now we are back on G-Power, and based on what we just learned, we are going to estimate 3 sample sizes based on assuming that I have different levels of effect size. You can see that in G-Power I have 2 major sections, one that they call input parameters and one that they call output parameters. So here is where we are going to enter some of the parameters that we are going to be guessing or that we know from previous experience may be related to the specific example that we are trying to run. You can see that here we have options for 1 or 2 tails. For now we're going to go with 2 tails, and then you can see that here it has the correlation. Notice that it is assuming that is the population value. Notice that it's using rho, and it also says H1. So this will be for the alternative hypothesis. Here we have the value for the alpha, so we can change this to any alpha that we want to be using. We have our power, and we will have the correlation for the null hypothesis, which in this case will be 0. As I said before, what we're going to be doing is setting 3 different effect sizes. We said, or not we, but Power, Cohen suggested that for low effect size, we assume that we have a correlation of 0.1. So we are going to change this to 0.1. And they also said that the power that is considered the standard value will be 0.8. So I am going to change this to 0.8. And now all I really need to do is to click on calculate, and it will give me the sample size that will be associated to that. So you can see that after I click on calculate, something happened. First of all, we got 2 distributions. One that is the distribution for when the null hypothesis is true, and one that is for when the null hypothesis is false. You might remember that we were talking about these 2 distributions in the video that you were supposed to be watching before getting into this part. The other thing to notice is that now we have some information here. So you can see that is providing me with a lower critical R. So this will be for something similar to a confidence interval, and an upper critical R. So this is basically saying that the correlations will be very, very low, and it will go between minus 0.07, technically 0, and 0.07. And the other thing that it will give me is the actual power, which is 0.8, and also the total sample size. This is really the part that we are interested whenever that we are doing an a priori power analysis, because this is going to estimate how big I need to have my sample in order to see the change that I expect to see. So as you can see from this example, having a very small effect size means that we really need to collect a lot of subjects in order to get something that may be significant. So now let's go and change this. So now we are using what we consider a medium effect size. And you might remember from the document that I shared with you and that I showed to you earlier that a medium effect size will be considered 0.3. So I am going to change this from 0.1 to 0.3. And notice that when I did that, the windows that I had here and the output that I had disappear, which basically is saying that G-Power is ready to recalculate the values. So I click on calculate again, and let's see what happens. The most important for you to pay attention after we do change the correlation from 0.1 to 0.3 is the sample size. You might remember that before, when we had a low effect size, the number of cases that were estimated was 782 cases. So now that we move from a low effect size into a medium effect size, you can see that the new sample size is 84 cases. So there is a big change in the number of cases that we need based on the effect size estimate. Finally, what we're going to be doing for this part of the video is to change once more the effect size by going into 0.5. So this will be in Cohen and Cohen's terms a high effect size. And we will keep everything the same. You notice that when I change this value from 0.3 to 0.5, everything disappears. So once more, G-Power is ready to estimate the sample size that we need. And so when we click on calculate, you can see that there are some major changes in this value. Once more, concentrating only on the sample size, you can see that now the sample size is 29 cases. So instead, it actually went from 782 to 84. and now only 29 cases. This demonstrates to a very large extent the importance of the effect size on changing the total sample size that you need. So based on the lecture that I shared with you, you can see the video. You might remember that there were some other ways to change power. Some of them were related to having a different alpha or the power, or so we can or the number of tails. So what I will do is just for the medium effect size play with some of these parameters so you can see what is the impact of changing some of these parameters on the total sample size that you need to get. So if I change the correlation to 0.3, because that will be the median effect size, and now I change from 2 to 1, let's see what happens. You will notice that when I change from 2 to 1, the sample size changed. When I had 2 tails, the value was 84, and now with 1 tail, it's only 67. So I'm gonna ask you to think about why that might be. Now I'm gonna change my alpha to 0.01, and I'm gonna go back to 2 tails. And now let's see what happens. So now you can see that the total sample size is 125, and I'm gonna ask you once more to try to explain why we have this change. Finally, I am going to go back to an alpha of 0.05, but I'm going to change the power from 0.8 to 0.95, and I'm gonna calculate the values again. And you notice that the new value is 138. And once more, I'm going to ask you to try to explain why is it that we have that change in the sample size. We said that the other thing that was very important about power is not only how to calculate the sample size, but also to calculate what happened once that you concluded the analysis and you want to know what kind of power you got. From the reading, you know that it is suggested that we need to have about a power of 0.8, and that is what we're going to hope that we can accomplish. So whenever that we are calculating power, there are a few steps that we need to follow in order to calculate power. The first thing that we need to do is to determine the effect size, or what will be the correlation in this case in the population. Next, we will determine what was the alpha value and whether it was 1 or 2 tails. Finally, we will determine what was the sample size that we use in the study. Once that we have all of that information, we can go and compute what was the power associated with the study. One thing that you might remember that we need to do is to change the type of power analysis. So far, we have been using the a priori, and now what we're going to be doing is using the post hoc. In other words, we know that we run the analysis already, and all we need to do is to know what was the power associated with the study. Just like I did when I was calculating the sample size, this time I'm going to be doing some changes to the effect sizes, the alpha value, and the sample size that we had. And so the first thing that I'm going to change is the correlation. I'm going to assume that the correlation in the population is 0.1. I'm going to assume that I have an alpha of 0.05 and that the sample that I used was 50. So with all of those parameters set, now I'm going to click once more on calculate and see what happened. As you can see from the output parameters, the power is only 0.106. That is a very small power, and what this is basically saying is that chances are that I will not be able to detect it and to reject the null hypothesis because I do not have enough power to reject it. As I was saying, Cohen and Cohen suggest that we should have about a power of 0.8 0.8 to be able to detect a significant change. So what will be the bottom line in this case? That perhaps we need to change the sample size. Perhaps we need to collect more data in order to be able to detect this effect that I'm trying to detect. So now let's say that instead the correlation in the population is in fact 0.3. And let's see, we're not going to change anything as far as the sample size or the alpha. And let's see if we can get an estimate for the power with this combination of the correlation and the sample size. And now we get that the value is 0.57. One way to interpret this 0.57 will be that my probability of rejecting the null hypothesis when the null hypothesis is in fact true will be 0.57, which you may think is high, and you may decide that that is enough for you to go on and conclude your study. But most people, as I said before, based on Cohen and Cohen's approach, will think that you would rather have a power of 0.8. So let's see what happens if now we change the value for the correlation, and now we say that in fact the real value was 0.5 and my sample size is still 50. When we use these numbers instead, you can see that now my power actually is larger than 0.8. Now it is 0.967. So what this is saying is that my probability of rejecting the null, if the null is true, is 0.967, which is pretty good. In fact, some people will say that you really had a sample size that was bigger than what you needed. Now we are going to explore how to calculate the sample size for a simple regression model. And the first thing that we need to do is to change here to the option of linear bivariate regression, one group size of slope. And you can see that the options that we have for input parameters and for output parameters change from what we had when we were using correlation. So there are things here that are important for us to understand. The first one is that the slope, here it is suggesting the slope under the alternative hypothesis. It's including the alpha value, the power. It's also including the slope under the null hypothesis, which most times will be 0, but you can change that. And it's also asking for the standard deviation of x and the standard deviation of y. You may not necessarily know some of these parameters, so you may have to guesstimate, for example, for the standard deviation of y and the standard deviation of x. Similarly for the slope under the alternative hypothesis. The other things that you see will change is that now it's giving me a non-centrality parameter. Some of this information is presented in the notes for this week. Also the critical t, the degrees of freedom, the total sample size, which is what we're going to try to estimate, and the actual power. In the handout that I added to explain the use of g-power, I speak about the fact that Cohen and Cohen suggested that you use that you compare these to standardized regressions, because then they can be manipulated as if they were correlations. But the manual that was recently developed by g-power has a slightly different idea. They say that you can just enter the slopes for some of these values, and I will also illustrate some other option in just one moment. So let's just say, for the sake of demonstration, that you have some information that will make you think that the slope for the model that you are trying to run will be 0.15. What will be the sample size that we will need if we were to use a power of 0.8? So to calculate that, all we need to do is to click on calculate and it will give me the information that I need. You can see that based on this hypothetical data, the sample size that I need will be 270 cases. One other important thing to notice is that the tail will be a one tail. And why is that? Is because you are assuming that you know if the relationship between the independent and the dependent variable will be positive or negative. So there is no need for you to waste any power calculating this for a two-tailed test. Now, it's very likely that you will say to yourself, well, but I don't really have any way to know what will be the slope. I may have an idea about the correlation. So, if that is your approach, then G-Power has your back. Notice that here we have an option to determine. So I am going to click on that and you will notice that it opens a new window. In this new window, you can see that you can enter the correlation, but you will also need to enter the standard deviation of the residuals. So not a full free ride, but perhaps you will have a way to know what might be an estimation for the standard deviation of the residuals. So say that you determine that the correlation between the independent and dependent variable is 0.3, a medium effect size, and you happen to know that the standard deviation of the residual will be 0.5. So if you have these two values, we can click on calculate and you can see that it will give me some specific parameters. Now, this in itself will not be very useful unless you notice that here we have the option to calculate and transfer to main window. So when we do that, you will see that the values here have actually changed. Perhaps not too much, but enough that perhaps we'll be able to make a difference. So now that we have these new values here, we can recalculate the value and you can see that now the total sample size actually went back to 64. Now we are going to try to estimate the power given that we have some specific information in my parameters. So the first thing that we're gonna do, as I did just here, is to change from a priori into post hoc. And you can see that it's already giving me some values. This is based on the data that I had from before. So let's just say that instead of having a slope of 0.15 something, I'm going to stick with a slope of 0.15. My alpha is still 0.05. I can set that this time my sample size is 50 and that my standard deviations one more are 1 and 1. So given this information, what will be the power? So you can see based on my calculations that the power will be 0.267 or rather 0.278. And what this is basically saying is that I do not have enough power. In fact, the probability that I will be able to reject the null if the null is true is 0.27, which is not a lot, is not a high probability. Just like we did before, we can estimate the slope based on correlations. And so what I'm going to do now is to once more open that part of G-Power so you can see how we can potentially do that. So let's say that I know that the correlation in the population is 0.4 and that the standard deviation of the residuals, which once more I will need to know, but this time I should know that information because what I'm doing is calculating power. So this suggests that I already ran the model. So let's just say that I stick once more with the standard deviation of 0.5 and based on those two parameters I can estimate what will be the value for the slope and the standard deviation of y. So as you can see, I have some estimates, and I once more can calculate and transfer to the main window. So you can see that when I do that, some of these values change based on what I have here. And now once more I can calculate the value, and you can see that this time the power has increased to 0.91. Now you can think for yourself, how can I possibly come up with all of these guesstimates? And I think the best answer for that will be, that is why you can do sometimes some pilot work, some pilot studies. So the way that it will operate is that perhaps you can start doing some pilot studies, or you can find out from the literature what will be some potential values for that. And the cycle perhaps will be to start by calculating the power associated to this pilot work that you did, or some potential guesstimates that you get from looking at the literature, and then based on that you will know what is your power. Now if your power is under 0.8, perhaps what you will do is to use those values that you initially started with and try to calculate what will be the sample size that you need in order to get a power of 0.8. So although this sounds really overwhelming, it is not so much. It's just a question of thinking about these potential options. Okay, finally we are going to learn how to calculate power for a multiple regression case. The first thing that we are going to do is to go into the test menu and then go correlation and regression, and then try linear multiple regression fixed model R-squared deviation from 0. So you can see that when I do that, I have a change once more into the input parameters and the output parameters that I have options for. You will notice that in these new input parameters we have something called effect size f to the square, which is not something that we had seen before, but I do have in one of the handouts that I have for you for this week. You will see what this f squared is, and here is the part of the handout that I'm referring to. So you can see that here we speak about a sample size, and we said that we need to calculate R squared, but the way that we're going to determine the effect size, which is associated with R squared, is by computing this value f to the square, which as you can see from this equation is just R squared divided by 1 minus R squared. So you may be thinking to yourself, here we go again, I need to start using my calculator and find these values. Well, in this case you don't need to worry about that, because once more G power using this determine option will let you calculate those values for you. As you can see from this new menu, one of your options is that you can enter the correlation coefficient, the multiple correlation, but you need to square that value. So what I did in this particular example is to try to estimate the effect size, assuming that the multiple correlation will follow the guidelines provided by Cohen and Cohen of 0.1 for a low effect size, 0.3 for a medium effect size, and 0.5 for a large effect size. Now if you multiply 0.1 times 0.1, the value to the, or raise that to the square, the value that you get is 0.01, which is the value that I have here. So once that I do that, I can calculate my effect size, which is this value that you see here, and I can just transfer that value to the main window, which is what I did earlier. So you can see that here it is saying that my effect size is 0.01010101. I set my alpha to 0.05. I set my power to 0.8. That's the standard, as you might recall. And in this particular case, I said that I have 3 predictors. In other words, this model has 3 independent variables. With all of that information, then I can calculate the output parameters that I have here. So the important value to pay attention to will be the total sample size. And as you can see here, if I want to keep a power of point A and I have an effect size that is 0.01, then the sample size that I need to select will be 1084 cases, which is probably a bit too high. You may have to spend a few years collecting that kind of data. So let's see now what happens if instead of having a value of 0.1, a small effect size, I were to raise that to 0.3. So 0.3 times 0.3 or 0.3 to the square will give me a value of 0.09. And once more I can calculate the effect size, which now comes to 0.0989. I can transfer that value to my main window. You can see that now I have that value here. Everything else will stay the same. I'm still assuming a power of 0.8, an alpha of 0.5, and the number of predictors will be 3. So I can calculate the value for that, and you can see that now my sample size will be 115. So clearly not as bad as having an effect size of 0.1. Finally, as far as this section is concerned, what if instead I had a high effect size? In other words, my correlation was 0.5, my multiple correlation. So if you raise to the square 0.5, the value that you get is 0.25. So let's see what happens when I calculate the effect size for multiple correlation to the square of 0.25. And so I have now an effect size of 0.333. I transfer that to my main window and I keep all the other parameters the same. And now I calculate my value and I find that my sample size is 37, which will feel like a relief if this was your dissertation. What if instead of trying to calculate the sample size, I was interested in calculating the power? So in that case, I need to go to the type of power analysis and change my option to a post hoc, which will allow me to compute the achieved power given a sample size and effect size. So notice that once more, what I need to do is to calculate my multiple correlation and enter my alpha, the sample size that I have in mind, and the number of predictors. So let's say that in this case I have once more a small effect size, and you might remember that we said that in that case it was a 0.01 for 0.1 to the square. So I want to calculate my effect size and then transfer that to my main window. Let's just say that this time I was a bit more assertive and I collected a sample size of 100 and that I have a number of predictors of 3. With this information, I will be able to find what are the numerator and denominator, and more importantly, the power associated to my model. So when I click on calculate, you can see that the power that I have is 0.1135. What this is that the probability that I will reject the null hypothesis when the null hypothesis is true is 0.11. Okay, so let's say that instead of having a low effect size, now I am going to assume that I have a median effect size. So my multiple correlation is 0.3, and when I raise that to the square, I get a value of 0.09. So what will be now my effect size? So here I can see that my effect size is 0.0989, And when I transfer that to the main window, I have once more my new effect size, and I keep all the other parameters to the same value. And when I calculate my new power, I can find that I have 0.73. Now, you might remember by now, or I hope that you might remember, that the power that is considered as the standard will be 0.8. So this is very, very close as what we will consider a standard power. And in fact, you may think that this is just enough for your study, and perhaps your advisor will be okay with that. Okay, so given these parameters that we have so far, you may say to yourself, I think that's enough. But just for greens, we are going to calculate once more what will be the power if we had a high effect size, which in this case you might remember we said that the multiple correlation will be 0.5 and the multiple correlation to the square will be 0.25. So let's calculate the new effect size and then transfer that to my main window. The effect size is 0.33333, and we are not going to change any of the other parameters. In other words, my alpha will stay at 0.05, my sample size is 100, and the number of predictors is 3. And let's calculate now what will be the value for the power. And as you can see here, the power is almost 1, so I can have close to a probability of 1 of detecting being able to reject the null hypothesis. The null hypothesis is false. So I think this is enough for this video. So I'm gonna stop here. There may be some other things that we may want to review later about power, but I think that for now we should be okay. I want to also let you know that I might have said in some sections and power or the probability that we have in this specific cell is the probability of rejecting the null hypothesis when the null hypothesis is true. That is incorrect. The power is the probability of rejecting the null hypothesis when the null hypothesis is false. Let me repeat that. The power is the probability of rejecting the null hypothesis when the null hypothesis is false. If you find that I said the opposite in some part of the video, I apologize. I just realized that I might have said that. Okay, so that's enough for today. Let's call it a day, and I will see you next week.